Okay, chemistry 2341. We're going to continue on with chapter 7, last section, part 6. Okay, now that we have the acetylenes and the alkenes made, let's go ahead and figure out what we can do with them. So the first thing we want to think about when we've already formed our alkene or alkyne is what would the next step be? And in this case right here, we're going to start with the acetylide ion. And the best thing we can do with the acetylide ion is actually the fact that this is the most acidic hydrogen available on a carbon. So if we can think back to our sp hybridization, making this the most acidic hydrogen, when we have an alkene, we have this carbon-hydrogen bond, and it's not very acidic. And then, of course, if we have the alkanes, we have the lowest pKa. The highest pKas in the 50, making them very poorly acidic because they are very, very strong bases. Okay, if we have a terminal alkyne, meaning we have a hydrogen on that alkyne, we can deprotonate that with a very strong base in an acid-base reaction. So if we think about it, we actually can make if we deprotonate that, we can form the acetylide ion. And these are very useful as nucleophiles. The issue here is we only can use very, very strong bases. Because the pKa of this is so high, we have to use something very, very strong. So hydroxide and alkoxides are not strong enough to do this reaction, so we have to use amide or hydride to be able to do that reaction to give us our acetylide ion. Okay, so let's talk about some of the reactions we can do with our acetylide ions. Once we form our acetylide ion, it is a great nucleophile. It can do SN2 reactions where it will displace out chloride reactions on alkyl halides, and it'll also do it on methyl halides to give us our chain extended new carbon-carbon bond. Notice we started with 2 carbons and 1 carbon here, and now our final chain has 3 carbons. Okay, this is our first reaction in which we've created a carbon-carbon bond. So this is very interesting point for us to be in right now. Now, it doesn't matter how long this chain is, as long as it's a primary alkyl halide, we can have us attacked by this acetylene ion using an SN2 function to give us our chain extended internal double bond, okay? So if we have it reacting with secondaries and tertiaries, unfortunately, this acts as a really strong base, and so we can end up with E2 elimination products. So we have SN2 if we have a primary or a methyl group, and then we start doing E2 products if we have secondaries and tertiaries because it's such a strong base. Okay, so what are some other reactions we can do with that? Well, once we form an alkene, the alkene is actually, this pi bond is the weakest part of this, meaning that if we added hydrogen across that double bond, number one, it's going to liberate heat because this right here is more stable than this right here. And so we're going to liberate heat. And so we can actually start comparing how stable things are by how much energy it gives off during that heat of hydrogenation. Okay, so hydrogen is a non-polar bond, so we really need to influence it to go ahead and add across the double bond. And we usually do that by adding a catalyst. And most of the time we use a catalyst that's palladium, platinum, or nickel. And the reason it works is it's actually adsorbed to the surface of the solid, and therefore it reacts all at once in a syn addition. Okay, so what do I mean by syn addition? Okay, since we have the metal surface here and the hydrogens are added to the surface here, what we're going to have to do is we're going to have the alkene come and lay on across that surface of those hydrogens to get those to react with the hydrogens on the surface. So both of the hydrogens are going to add on the same side. So that's our syn addition right here. So if we just had something like this ethylene right here and we added it across, we really can't tell where the hydrogens go. So we have to have another substrate that lets us show us where the hydrogens are. So if you look in this case right here, this double bond has to lay flat on the surface here. And the fact that the hydrogens are on the same side and give us the stereochemistry available here, that's proving to us that the hydrogens that we're adding across that double bond had to add on the same side because they sat, that substrate had to sit flat on that surface. Okay, so how does that work? Well, the first thing that has to happen is we have to have the hydrogen adsorb to the surface here, okay? And when you have a solid surface, then your alkene has to come down and start to settle on that surface such that it is close enough to react across those pi bonds, okay? Once those pi bonds start interacting with the surface, we can then form the new sigma bonds. Remember, the pi bond is a higher energy bond than the sigma bonds, and therefore it reacts spontaneously at that reaction surface to make those two new sigma bonds. Okay, so we have a different rates available to us in this catalytic hydrogenation, and the mechanism of this explains the two facts about this. First of all, that it's a rapid sequential addition of hydrogen occurs on the side of the alkene complex to the metal surface. So it has to come down on the alkene first, okay? So then the other thing it is that the less crowded that double bond is, the easier it is for it to come down on this surface. So that when we have a terminal alkene, that's the easiest because you only have the one R group that's forcing it away from the surface. The trans is next because you can have the two groups farthest away from each other trying to come down on that surface. The cis is less reactive because you have both of these groups having to come down on the same side. And then as you get to tri and tetra substituted, those are even more and more, okay? So if you look here on this species here, the primary or single substituted is first, the double substituted, preferably trans, is next, the tri-substituted is next, and then the tetra-substituted is next. It's all about getting all four of those R groups to come and sit flat on there. Okay, so how can we reduce alkynes? Well, we have a couple different ways to reduce alkynes. The first kind is to use catalytic hydrogenation. Just like with alkenes, the alkyne is a pi bond, and so it's going to react with the first double bond, the first pi bond, then the second pi bond to give us our alkane, okay? And there's no specificity. It doesn't really stop because remember that catalytic hydrogenation already reduces alkenes. So if you have an alkyne, it's going to reduce the first double bond, then the second double bond down to the alkyne. So let's say you wanted to stop at the alkene from the alkyne. Well, here we have to do what we call a Lindlar's class or a poisoned catalyst. We need to make the catalyst not work so quickly, and therefore to do this, we're doing what we call Lindlar's catalyst or using this nickel borate right here. So in a Lindlar's catalyst, we actually take our platinum catalyst and add lead to it. And so lead is Pb. Right here. And so by adding this lead to the thing, we call it poisoning the catalyst. And when we do that, we end up with the cis alkene always, because we get syn addition across here. Remember, whenever we have it coming across the flat surface, we get syn addition of hydrogens because the hydrogens are on the surface here. We get the cis alkene because of that syn addition. Okay. The other way to do that is to do what we call a dissolving metal reduction. And in this case, we take sodium metal and we take ammonia. But when we do this dissolving metal reduction, because of the mechanism, we end up with a trans addition, okay? So whenever we have our catalytic hydrogenation, it's syn addition. If we poison our catalyst with we can take an alkyne to the cis alkene. And if we want to stop again at an alkene, but we started with an alkyne, and we want the trans configuration, we have to use what we call the dissolving metal reduction. Okay, so let's look at those mechanisms a little in more detail right here. So since the palladium on with hydrogen on it produces alkenes, we cannot stop. It goes all the way. So then to stop the reactivity, what we're going to do is we're going to add a little lead acetate to the system and quinoline. And what those do is those take some of the reactivity out of the catalyst so it stops at the cis alkene. The other way to do this is to use this nickel borate, which then creates a little bit of this hydrogen at the surface. And because of that, we can get, again, syn addition. It's adding across here, which will give us our cis alkene. So this is in contrast to our next thing, the dissolving metal reduction. In the dissolving metal reduction, we have sodium right here, or in the case of this mechanism here, lithium actually oxidizing down, transferring a single electron to the system to create a vinylic radical and a radical anion. Okay, so let's do this step by step. We have the metal right here that has one electron in its outer shell and it wants to give it up to become a +1 metal. When it does that, it gives its electron to this pi bond, giving us a full negative charge on one side of the species and giving us a radical on the other side of the species. Okay. This now anion acts as a base and can pull a hydrogen off the solvent. In this case, it's ammonia or this amine right here. Once it does that, the radical can then react with another equivalent of the lithium or the sodium to create another ion. This now becomes the base and will deprotonate again. Notice because of the R groups trying to be opposite each other, trying to be in the trans configuration, we end up with the anti-addition of the hydrogen across the system. This is completely the opposite of the syn addition because we have the formation of this radical anion acting as a base and then this anion acting as a base. So we end up with this trans addition of the hydrogen. And that's the way to get to this trans alkene from an alkyne using that dissolving metal reduction. Okay. So let's do an example of retrosynthetic synthesis. So depending on which one we want to form, we want to start figuring out how we're going to add certain carbon molecules and how we're going to either break them down. So let's look at this one right here. So if we were trying to make this compound, what would we start with to do it? So we can add this right here with a Grignard. We can add this as an acetylide, and we have this right here. But if we were to add that as another thing, we want to think about that's a secondary carbon. This is a primary carbon. So we probably want to compare and contrast the primary versus the secondary carbon and see if we might accidentally do an elimination reaction. So by thinking of it backwards, we don't want to form the, we don't want to use the acetylene on a secondary carbon because that will make sure that that'll give us an elimination product. So the key is we have to have this group on the acetylene first, or else it will eliminate. So our plan here is to get the acetylene on the cyclohexane first, then we can deprotonate this, and now we have a good anion and we have a primary alkyl halide to react with. So that means that we're going to have the secondary carbon already bonded to the alkane, and then we have to deprotonate the end, use it as a good nucleophile on a primary halide to give us our final product. Okay, so as we go through some of the problems in the back of the chapter, we want to think about, okay, now we have a lot of different reactions in there about what reactions compete with which reactions. And that's where we're going to start to think about how we can build these reactions very precisely and very efficiently.